Have you ever been deep in a coding project, convinced you've built something brilliant, only to realize that when you try to use it somewhere else, maybe a different project, maybe just another part of the same one, it suddenly turns into this tangled mess?
Oh, yeah. That dream of saving time by reusing code,
Hmm.
it can quickly become a debugging nightmare.
Exactly. You just wanted one simple component, but suddenly it feels like it's pulling in half your code base with
Yep. Know the feeling.
it. Welcome to the Deep Dive. We're the place where we unpack source material articles, research notes like these, to pull out the really important nuggets of knowledge and insight for you.
And today our mission is to take a deep dive into reusability, specifically how it's laid out in the Ada Quality and Style Guide.
Right. And this isn't just, avoiding copy-pasting code. It's really about crafting software components that are so well designed, so flexible, they become these enduring assets you can use across lots of applications.
We're going to unpack the core characteristics that make code truly reusable, drawing on the practical guidelines and maybe some surprising insights from the Ada world.
Okay, let's get into it then. Reusability.
Right.
It's a goal pretty much every developer aims for, right? But what does it actually mean in practice? Especially when you're talking about a structured language like Ada.
Well, what's fascinating here is how the Ada Style Guide actually defines it. It says reusability is the extent to which code can be used in different applications with minimal change. Minimal change, that's the key.
So not just copying and pasting.
Not at all. It's about designing components so intelligently that they almost automatically get qualities like maintainability, portability when you reuse them. And the guide, interestingly, focuses purely on the technical side of writing reusable Ada parts.
Ah, so it leaves aside the sort of managerial or economic headaches that often come up with reuse.
Exactly. It zeroes in on the how-to from a code perspective.
Yeah. Okay, so if we're focusing on the technical nuts and bolts, what are the foundational ideas? What are the pillars that make code genuinely reusable in Ada, according to the guide?
It lays out 4 key characteristics,
Yeah.
really important ones. First, the reusable part has to be understandable, like really clear.
Okay, makes sense.
Second, it needs to be of the highest possible quality. That means correct, reliable, robust. Basically, it works properly and doesn't fall over easily.
Got it.
Quality. Third, it absolutely has to be adaptable. It needs to work in different situations for different needs.
Flexible.
And finally, it needs to be independent. You don't want to pull in a massive library just for one tiny function, right?
Right.
It shouldn't have unnecessary baggage.
Definitely not. Okay, so understandable, high quality, adaptable, and independent. Let's maybe dig into each of those. How does Ada help achieve them?
Perfect. Let's start with the first one, understanding and clarity.
Right, this seems kind of obvious for any code, reusable or not. So what's the specific angle here for reusable components in the Ada guide?
Well, it's paramount. For reusable parts, it's even more critical that it's immediately obvious what they do, how you use them, and maybe even a little about how they work internally. The guide really doubles down on general readability guidelines here.
So extra clear.
Extra clear. And one key aspect of that is application-independent naming. The guideline is basically pick the least restrictive, most generic names you can.
Generic how?
Generic in that the name shouldn't tie it to one specific use case. It should hint at the behavior, not the application. And it shouldn't clash with names you might use later when you instantiate it.
Can you give an example? That sounds a bit abstract.
Sure, let's say you're making a generic stack package. Instead of just calling it stack, the guide might suggest bounded stack.
Okay, bounded stack. Why bounded?
Because that describes a key behavioral characteristic. It has a fixed size.
Mm-hmm.
Then when you reuse it, you could instantiate it as, say, tray stack in one application, or maybe invoice stack in another.
Ah, I see. The generic name stays general and your specific use case name gets added later.
Exactly. It encourages reuse because the base name isn't already taken or too specific.
Yeah.
And adding that behavioral hint, like bounded, helps tell it apart from maybe an unbounded stack you also have.
That makes a lot of sense. Keeps things clean. Now, you mentioned clarity. What about abbreviations? We use them all the time. Things like GMT.
Ah, yes. This is where the guide gets, let's say, very clear. It strictly advises avoiding abbreviations in identifiers or unit names for reusable parts.
Strictly. Even really common ones like GMT.
Even GMT. The example given is preferring Greenwich Mean Time over GMT in a general-purpose package spec.
Wow. Okay, I can almost hear some developers thinking, but everyone knows GMT. Is that maybe taking it a bit too far? Or is there a hidden danger?
It's a great question. It might feel a bit pedantic, But think about the goal.
Hmm.
Maximum reusability across any context. GMT might be obvious in a timekeeping context, but what if that component gets pulled into a logistics system where GMT means something totally different? Global manufacturing team, maybe.
Okay, fair point. Context is everything.
Precisely. A truly general component needs to shed all that domain-specific shorthand. It's about striving for that context-free universality.
Understood. So clear names, no abbreviations. What else under clarity?
The guide also really stresses documenting generic formal parameters. Ada's generics are super powerful, letting you parameterize types, functions, values. But not every assumption you make about those parameters can be written directly in the code.
So you need comments to fill the gaps, like a contract.
Exactly like a contract. If you have a generic quicksort procedure, you need to thoroughly document what you expect from the index type, the element array, the should proceed comparison function, the swap procedure, all their obligations.
So the person using your generic knows exactly what they need to provide and what rules they need to follow.
Yes, the generic specification is the contract. Clear documentation ensures both sides understand the deal for it to work correctly, avoids nasty surprises later.
Right. Okay, that covers clarity. Let's move to the second pillar, robustness. Reusable code needs to be tough, right? Able to handle unexpected situations or misuse.
Absolutely. Robustness means the code defends itself. Because when you reuse something, it might end up in an environment or be used in ways the original author never imagined. Subtle assumptions can break things.
How does Ada help build in that defense?
One really neat technique is using named numbers and static expressions. The idea is to link lots of dependent values back to just a few core symbolic constants.
Like defining constants for key parameters.
Exactly. Imagine a disk driver. You define constants like number of sectors, number of tracks. Then other values, maybe total capacity, could be calculated from those constants.
So if the hardware changes, you just update the core constants.
Precisely. Change one number and all of the dependent declarations update automatically. It makes adaptation for reuse way easier, cuts down errors, and it kind of self-documents the relationships between values.
That's really elegant. What else?
Another big one in Ada is using unconstrained arrays. The guideline is to use unconstrained array types for formal parameters, and also for function return values.
What does unconstrained mean here?
It means the size isn't fixed in the type definition. So a procedure can accept an array of any size. And crucially, local variables inside that procedure can then be declared to match the size of the actual array that was passed in.
Oh, wow. So if I have a matrix operation, the temporary workspace arrays inside can automatically size themselves based on the input matrix.
Exactly that. It automatically handles size changes without you needing to modify the procedure's code. Makes the component incredibly adaptable.
That sounds powerful, but maybe a bit more upfront work for the person writing the reusable part.
Maybe a little more thought initially to design for that generality, yes. But the payoff for the person reusing it and for future maintenance is huge. You're catching potential size mismatch errors at compile time, not as runtime crashes.
Makes sense. Better safe than sorry. Now, you mentioned subtle assumptions. That brings us to something you hinted could be a pitfall. Subtypes and generic specifications. What's the issue there?
Yes. This one can really bite you if you're not careful. Let's say you define a generic parameter with a subtype constraint, maybe range 1 to 10. You think you're telling the generic, only expect numbers from 1 to 10.
Okay, seems reasonable.
But then someone instantiates your generic using their own subtype, maybe range 1 to 30. Age's rule is that the constraints of the actual subtype, provided at instantiation, are the ones enforced at runtime.
Wait, so the range 110 in the generic definition is ignored at runtime?
Essentially, yes, for enforcement. The actual subtype's constraints, 15.3 in this case, take precedence. If your generic's internal logic assumed values would always be between 1 and 10 based on the formal parameter declaration, you could get a constraint error at runtime when it encounters a value like 15.
Ouch. That's subtle. So the generic definition is more like a suggestion, and the instantiation is the real deal.
Kind of. It highlights that you need to be careful about assumptions. The best practice is often to use attributes like first and last inside the generic to work with the bounds of whatever type is actually passed in, rather than relying on the formal subtype constraint. And document assumptions clearly.
Good tip. So avoid hard-coded assumptions based on the formal generic subtype. What about overloading? Can that cause robustness issues in generics?
It can. The guideline is, be careful about overloading subprogram names exported by the same generic package. Imagine a generic input-output package. It exports two procedures named put. One takes an integer, the other takes a generic type item.
Okay.
Now, what happens if someone instantiates that generic package with item being integer?
Ah, then you have two put procedures that both take an integer. The compiler won't know which one you mean. Ambiguous.
Exactly. It leads to ambiguity and means the package just can't be used with certain types, which limits its reusability. So avoid that kind of overloading in generics where possible.
Right. Keep things distinct. What about hidden complexities, things happening behind the scenes like tasks?
Good point. Hidden tasks are another area needing care for robustness. If withing or using a package specification automatically starts up background tasks, that needs to be clearly documented
Why is that so critical?
because tasking dramatically affects real-time behavior, performance, potential race conditions, all sorts of things. The user needs to know if your reusable component suddenly introduces concurrency, and especially if generic formal parameters are accessed by these hidden tasks. Documentation is key to allow proper analysis.
Makes sense. And finally, under robustness, exceptions. How should reusable parts handle errors? Just catch everything.
Generally, no. The guideline is actually to propagate exceptions out of reusable parts. Only handle an exception inside the reusable part if you are absolutely certain the handling is appropriate in every possible context it could be used.
Why not handle them? Isn't that safer?
Not necessarily for reusable code.
Mm-hmm.
The user of the component is usually in the best position to decide how to handle an error based on their specific application's needs. What might be a fatal error in one context could be recoverable in another.
So the reusable part should focus on its job and signal problems clearly if they happen.
Exactly. And if it does catch an exception, maybe from a generic subprogram it calls, it must ensure cleanup is done properly. Critically, it should leave any state variables or parameters in a valid, consistent state, preferably unmodified from before the operation started, before re-raising the exception.
Like an all or nothing operation?
Precisely. Aim for that transactional feel. No half-finished states if an error occurs. It maintains predictability.
Okay, that's a solid look at robustness. Let's talk about adaptability. This feels central to reuse. How does the guide suggest making Ada code easy to mold for new situations?
Right, adaptable parts need to be easy to change, ideally locally, without digging into the core logic. It often means providing general functionality that you can then extend or configure.
How do you provide that general functionality effectively?
Well, first, aim for complete functionality in the core abstraction. Provide the essential operations. For dynamic data structures, this absolutely includes things like initialization and, crucially, finalization or cleanup routines. Think about using ada.finalization.controlled types.
To prevent memory leaks and stuff.
Exactly. A reusable queue abstraction, for instance, should probably offer operations like setInitial maybe, definitely eyesFull or eyesEmpty, but also a cleanup operation to release any dynamically allocated memory. It makes the abstraction self-contained and prevents resource leaks when it's reused.
Makes sense. And Ada's big tool for adaptability is generics.
Absolutely. Leveraging generic units is key. Use them to avoid duplicating code for different types. Parameterize everything you reasonably can, types, subprograms, values to maximize adaptability. A single generic unit can serve many specific needs just by how it's instantiated. Maintenance is centralized too.
When you define these generics, how do you handle the types you're parameterizing? You mentioned private types earlier.
Yes. The choice of formal, private, and limited private types is important. If your generic needs assignment internally, use a non-limited private type. If it doesn't need assignment, use limited private. If you need special cleanup or assignment behavior, consider ada.finalization.controlled.
Why is this choice so important?
Because it explicitly states the assumptions the generic makes about the types it operates on. Using limited private when you don't need assignment signals the restriction, ensuring the generic can be used with types that don't support assignment. It protects the integrity of the data structures, too. Export the least restrictive type possible that still guarantees correctness.
So it's about clearly defining the interface contract again. What about algorithms? Can we make those generic too?
Definitely. Encapsulating algorithms with generics is a powerful technique. You write the algorithm once, generically, independent of the specific data types it works on.
Like it's an example.
Exactly. A generic sort procedure would take the element type as a parameter, the data array type, and also the comparison should proceed, and swap operations as generic parameters. Then you can instantiate that same sort of logic for integers, strings, records, whatever, just by providing the right parameters. Highly reusable.
That decouples the logic from the data nicely. Now, you mentioned a really interesting distinction earlier, Abstract data types, ADT, versus abstract data objects, ADO, especially with generics. Can you break that down again? It sounded important.
It's a really fundamental concept for structuring reusable components, especially data structures. An ADO, an abstract data object, is like having a single instance of something. Think of a package that manages one specific stack, and that's it. You can't declare another stack of that kind.
Okay, like a singleton pattern almost?
Sort of, yeah. Now, an ADT, abstract data type, is different. A package exports a type. So users can declare multiple variables of that type. You could have an array of stacks, past stacks as parameters, and so on. Much more flexible.
So ADT is generally better than ADO for reuse.
Generally, yes. But Ada takes it further with the generic abstract data type, GADT. This is where you combine generics with the ADT approach. The generic package exports a type, and it's parameterized.
Ah, so you get the best of both worlds. Multiple instances, and they can be customized via generic parameters.
Precisely. That bounded stack example we talked about. A GADT version would let you instantiate it for any element type and potentially even specify the bound, the size, as a generic parameter. You could create trace stack of size 50 and invoice stack of size 1000, both from the same generic source. It's the most powerful and flexible approach for reusable data abstractions.
And the guide suggests the complexity isn't much higher than an ADO.
Surprisingly, often not. The structure is very similar, but the payoff in flexibility is enormous, so the GADT is usually the way to go.
Okay, GADT is for the win. What about accessing elements within complex data structures? How do we do that without breaking encapsulation?
That's where iterators come in. For complex structures like lists or trees, you should provide iterators to allow users to traverse the elements.
What kinds of iterators?
The guide suggests providing both passive and active ones if possible. A passive iterator is often a procedure that takes another procedure as a parameter. It hides the traversal logic and just applies the user's procedure to each element.
Okay, like a for each kind of thing.
Exactly. An active iterator, on the other hand, exposes the traversal steps. Think operations like initialize iteration is more elements, get next element. It gives the user more control.
What's the catch with iterators?
The tricky part is handling what happens if the underlying data structure gets modified while an iteration is in progress. You need to design them carefully to either prevent this, detect it, or at least clearly document the behavior, like the iterator becomes invalid.
Right, concurrent modification issues. Important to document. What about adapting to different human languages or regions, like currency?
Yes, decimal type output localization is crucial for adaptable financial or international software. Ada's AdaText.io.editing package helps here. The guideline is to make things like currency symbols, digit separators, comma versus period, radix marks, and fill characters configurable.
So you can instantiate the same output logic, but configure it for dollars, euros, yen.
Precisely. You can instantiate decimal output multiple times, each configured differently. It allows easy adaptation to diverse display conventions without changing the core logic.
And one more advanced concept, mixins. How does Ada approach composing functionality like that?
Ada uses a combination of abstract tag types and generics for mixins. The idea is you define reusable chunks of functionality in generic packages that operate on abstract tag types.
How does that work?
Imagine a generic package P. It takes an abstract tag type S as a parameter and exports a new type T, which is an extension of S, adding some new behavior or data. You can then chain these together. Instantiate P with a base type S to get T1. Instantiate another mix in generic Q with T1 to get T2, and so on.
So you're layering functionality piece by piece.
Exactly. It creates this linearized succession of overriding subprograms, allowing you to compose new behaviors modularly by extending existing tag types. It's a very powerful pattern for building adaptable systems.
Okay, adaptability is huge. That leaves our final pillar, independence. We want reusable parts to be lean, right? Not dragging in unnecessary dependencies. How do we achieve that in Ada?
Independence is all about minimizing that extra baggage. A reusable component should ideally stand alone or only depend on things that are absolutely essential and clearly beneficial.
How can we structure code to help with that?
One key technique is subsystem design with child packages. Structure your subsystems so that the core, context-independent functionality is in a parent package. More specific, perhaps optional operations go into child packages.
So users can just with the parent, or the parent plus only the specific children they actually need.
Exactly. They don't have to compile or link against parts of the subsystem they aren't using. It allows selective reuse and avoids pulling in extraneous stuff.
That helps manage the code with clauses. Are there other ways to reduce dependencies, especially those with clauses?
Yes. Using generic parameters to reduce coupling is another big one. Instead of having a procedure with a specific package A to call a function inside it, make the procedure generic and pass that function in as a generic, formal subprogram parameter.
So the dependency moves from the reusable unit itself to the point where it's instantiated.
Precisely. It makes the generic unit itself more independent. You can also use generic formal package parameters to import operations from other generics without within them directly in the spec. It gives you much finer control over dependencies.
Interesting. What about dependencies related to compilation order? Sometimes things need to be compiled in a specific sequence, right?
Absolutely. That leads to coupling due to pragmas, specifically pragma elaborate body. If a generic unit's body needs to be elaborated, initialized right after its specification, perhaps because of complex dependencies or initialization requirements, you should put pragma elaborate body in the generic unit's specification.
Why in the specification?
Because it tells the compiler about this dependency early. It ensures the body is ready when needed, preventing potential program error exceptions at runtime caused by things not being elaborated in the right order. It's about managing those subtle elaboration dependencies for robustness and independence.
Okay. Now, what if you need slightly different versions of a component, like a bounded stack versus an unbounded one? Generics might not cover fundamentally different behaviors.
That's where creating part families comes in. If you can't achieve the variation purely through generic parameters, create a family of related parts. Bounded stack, unbounded stack, maybe synchronized bounded stack. They share a similar interface philosophy, but offer different core behaviors or implementations.
So the user can choose the family member that best fits their specific need.
Exactly. It provides flexibility and allows easy substitution if requirements change.
What about minimizing the actual code size that gets included? Can we influence that?
Sometimes, yes, through conditional compilation via dead code removal. If your compiler supports it well, you can structure code using, say, a case statement based on a Boolean or enumeration generic parameter. If that parameter is static, known at compile time, the compiler might be able to eliminate the unused branches of the case statement.
So you effectively get conditional compilation without preprocessor directives.
In a limited way, yes. The guideline is to structure code to take advantage of this when possible. It can lead to cleaner code than complex preprocessor logic, and the unused code paths just disappear from the final executable.
Clever. Are there other architectural patterns that promote independence?
Table-driven programming is a powerful one. Instead of hard-coding logic with lots of if or case statements, you put the varying logic or data into tables. The reusable code becomes a generic engine that interprets these tables.
Like a parser generator or a state machine interpreter?
Exactly like that. The core engine is highly reusable, and all the application-specific behavior is in the data, the tables. It's often very efficient and incredibly adaptable and independent.
And seems like we should leverage what Ada already provides too.
Absolutely. Using predefined string handling packages is a prime example. Ada has standard packages for fixed, bounded, and unbounded strings. Ada strings, fixed, bounded, unbounded, and character handling. Ada characters handling. Use them.
Don't reinvent the wheel for things like toUpperCase or trim.
Please don't. The standard library versions are portable, robust, and already there. Re-implementing them just adds code to maintain and potential portability issues. Stick to the standard where possible.
Good advice. And finally, for independence through generalization.
Use tag-type hierarchies. This is fundamental object-oriented design, really. Define a root tag type, like employee, and derive more specific types, part-timer, full-timer. Then write general algorithms like compute payroll that operate on the root type, often using pointers or references.
And polymorphism takes care of calling the right version for each specific type.
Exactly. The general algorithm works automatically with any type derived from the root now or in the future. You don't need to change the compute payroll code when you add a contractor type later. It massively decouples the algorithms from the specific data types, promoting independence and reuse.
Wow. Okay, so pulling this all together, we've gone through understanding and clarity, robustness, adaptability, and independence. Ada seems to offer a really comprehensive, disciplined toolkit for achieving reusability through these principles, naming, generics, types, exceptions, packaging.
It really does. And these aren't just, theoretical ideals. When you actually apply these guidelines from the Ada Quality and Style Guide, they genuinely transform components into these powerful, reliable building blocks. They do accelerate development and boost maintainability across different projects.
So that bounded stack you built for one system really can become a trace stack or an invoice stack in another system with genuinely minimal changes.
That's the goal. And Ada provides strong features to help you achieve it. It's about designing software that lasts, that earns its keep over time.
It definitely shifts the mindset, doesn't it? From just getting this feature done to how can I build this as an enduring asset? What's really interesting is how exploring these ADA-specific guidelines actually surfaces these kind of universal truths about good software design. What stands out most to you about designing for reuse in ADA? And maybe think, how could these ideas apply even beyond writing code? Something to ponder, perhaps. Consider how embracing these principles, clarity, robustness, adaptability, independence, maybe not just in code, but even in how you organize projects or structure arguments or even arrange your kitchen tools, could lead to more effective, reusable parts that save time and effort down the line.